Hi everybody, in this video we will talk about modeling viscoelastic materials, and this is an important concept for the biomaterials class. So what are viscoelastic materials? So these are materials that are basically, they have properties of both solids and liquids, right? And so they tend to have like these viscous and elastic behaviors when they undergo deformation, and these properties are basically a combination of fluid-like and solid-like properties. And these materials, they also exhibit time-dependent strain. Some common examples of viscoelastic materials include living tissues in the body, as well as certain polymers that can be constructed to exhibit viscoelastic behavior. So the way we create these models is we have different springs, and like for example we use springs to represent the solid-like properties, and we use dashpots to represent the liquid-like properties, right? So in terms of a spring, if you think about the stress and strain curve, right, you have stress is equals to the Young's modulus times the strain, right? So for example, if you were to imagine you put a solid, like a weight on a spring, and what it will do is like it will just pull it down, and then you have a certain amount of stretching that occurred, right? So basically the amount of stress that you had was proportional to your strain, which was how much it got stretched out, times the elastic modulus of the spring, right? But notice that, you know, stress is linearly proportional to strain. Strain is basically constant, right? But in liquids, that's not the case, right? So in liquid, what happens is you have this scaling factor, but it's a different scaling factor here. It's a viscosity, but you also have the strain, right? But the strain is not constant, so it changes with time. So the stress, it's proportional to the time derivative of the strain, right? So these are the two basically puzzle pieces that we use in the models when we want to model viscoelastic behavior. So in terms of models, we have three models, right? We have the Maxwell, Kelvin-Voigt, and standard linear solid model. So if you were to think about your, your physics 2 class, you have your circuits, right? You know how we say that we can put circuits together in a series manner or a parallel manner, etc. So basically these three models, that's how they represent these puzzle pieces that we have, right? So, you know, as I mentioned, the spring and the springs and the dashpots, these are basically you can think of them as your circuit elements. You can either put them in series like in the Maxwell model, or in parallel like in the Voigt model, or, you know, a combination of the two, right? So there's like a Maxwell arm here, and then you have your extra spring, right? So SL is like a combination. Okay, so when we look at Maxwell model, right, a property that's really important, so we look at what describes the stress and the strain, right? Because we want to find the best way to model viscoelastic behavior. So in the Maxwell model, we say that basically each element, it has the same stress. Okay, so basically, so going back here, right, so we see that both elements, they'll have the same amount of stress, right? And that's equals to the total stress in the system. But this total strain is different. So the total strain is going to be the strain from this guy and the strain from this guy. Combine them together, then you get the strain, right? And it's kind of the opposite system when you look at, so actually we'll talk about that in just a second. So when we look at how we model the equations, we have the total strain, and then we just sum them together. Whereas the stress is the same, right? And here we just have subscripts 1 and 2. So we can just look at the model and we can say either of these are 1 or 2. It doesn't really matter, right? So either your spring is 1 or your, in this case, the spring is 1 and dashpot is 2. But it can be the other way around too. But at the end of the day, it means the same thing, right? That for your strain, you're going to add them together, and for your stress, they're all equal to each other. Now, in terms of like generating the full equation to represent the strain, right, what we need to do is we're going to have to sort of kind of take the basic equations a bit further. So first what we're going to do is we're going to differentiate. So we're going to differentiate this equation. So we're going to say the change in in the rate of this property with respect to time, right? So here we just had the derivative of this property, which is the total strain with respect to time, and we did the same for the other two, right? And now what we're going to do is we're going to have to figure out these two values, right? These. So we're going to say the total strain experienced by the system is this, and it's equals to these two things. But then we're going to have an actual equation to represent what is this dE1 dt represent, which is, so one of these is representing the change in strain for the dashpot, and the other one for the spring. Okay, so so I know there's a lot going on in this equation, in this page, but okay, so first what we're going to do is we're going to look at the spring, right? So as I mentioned, for the spring, you look at your stress, and it's just the Young's modulus times the strain. So if you rearrange this equation for your strain, right? So you're going to get strain is equals to your stress divided by Young's modulus, but we want everything in terms of a derivative. So that's why we just put a derivative in front of the stress and the strain. But basically it's the same thing, right? So now we have an expression for one of those two things, right? So now we can plop this guy in here. And then we're going to do the same thing for the dashpot. So you're going to take your equation that I mentioned in the dashpot section, right? So your viscosity times the change in your strain with respect to time, rearrange for this guy, and then you have this guy, right? And then once you take this component and put it here, and take this component and put it there, then that's these two terms together represent your total strain that's changing with respect to time in the system, right? And you can do the same thing for the Voigt model. So the thing in Voigt model is you flip these properties around. Okay, so in Maxwell model, you had this type of thing where you're adding the two together to get the total stresses. Here, oh sorry, excuse me. So in the Maxwell model, each element had the same stress, right? But in this case, the total stress is not the same in each element. Actually, the total stress is the sum of the stress in each element, so it's not the same. But the strain is the same. So you just kind of flipped the equation around a little bit, right? So basically now the equations look like this. So notice we're adding the stresses together to get the total stress, right? Whereas if you go back to Maxwell equations, we said that the stress was the same. Okay, so and similarly, the strain is the same in this case. So I have a challenge for you guys. You have to come up with the equation for the Voigt model. The only thing is you don't need to do the differentiation here. Okay, so notice when we were here, we took these basic equations and we did differentiation. Well, in the case of the Voigt model, you don't really need to do that. So all you need to do is you're going to do a similar thing that we did initially. We find the two components to plug in for stress 1 and stress 2. But you don't need to differentiate it. So these are going to be the equations that are pertinent, right? So one corresponds to the dashpot, the other to the spring. You're going to rearrange it and just plug it in here, right? So if you complete this challenge, you're going to see that the stress is this, right? And basically, we just rearranged these properties, so we see that this is already solved for this, the stress of the dashpot, right? So you can just put that maybe in here. So we have that here on this side of the equation, and then this equation we just rearranged for the delta S, sigma S, right? So that's your stress of the spring. Now, SLS model is a little bit more kind of involved. Okay, so I kind of have everything sort of written out. So first what you need to do is you're going to do this stuff for your Maxwell arm, right? And then you're going to do like a parallel between this arm and this arm, right? So on this right side, that's the whole Maxwell side, right? So we see what the stress and the strain is in the Maxwell side, and then what we do is we combine the two together, right? So now we come here, we say that the stress between both of them, the strain between both of them is the same, and the stress is a combination, right? And this is because we're talking about both of them together, so that's a parallel system, right? So we sum them together. Okay, now there is this concept of creep, right? So creep refers to continuous time-dependent extension that occurs when a load takes some time to achieve equilibrium, elongation, and strain after you have applied a fixed load. And you see this occurring in metals and ceramics. It actually can occur at room temperature for polymers, and this can be best represented with the Voigt model, right? So you've applied your stress, and it will keep straining at different rates, and then this is the rupture point, and this is going to be the minimum creep. So you have like these 3 stages at which your strain is occurring, meaning that you've put the load and it's like keep getting elongated basically. So that's kind of what the creep refers to. Okay, you also have this concept of stress relaxation, and that gets that's best modeled with the Maxwell model. And basically, you're trying to stretch a material to a fixed length, and when you monitor the load, you realize that the stress actually declines continuously until equilibrium. Right, so you have this much amount of load, and then the stress is basically going towards this equilibrium. Okay, and yeah, so basically, so we have these 3 models, and when we look at these properties of creep and stress relaxation that are important in viscoelastic materials, you can best represent stress relaxation with Maxwell model and creep with the Voigt model. So I hope you find this video helpful, and thanks for tuning in.